Hello, and welcome back to Homework Help for Math 2. Today we're going to be looking at Unit 1, Lesson 4, Rabbit Run. As usual, we'll be starting with the Ready section. Directions here say, calculate the slope of the line between the given points. So for number 1, we are given the xy coordinates for 2 points. We want to know the slope between them. Slope is commonly referred to as m, or represented by m. This might look familiar from slope-intercept form, y equals mx plus b. Also, don't forget about point-slope form, y minus y1 equals m parentheses x minus x1. In both of those equations, m represents your slope. Now, conceptually, slope is the rate of change, which means it is the change in y. That's a Greek letter delta. That's a capital delta. In math, delta is commonly used for change. So it's the change in y over the change in x. Now, if we were given the graph, we could count the boxes. Rise over run is how that's commonly referred to. Graphing these points and then finding the slope would be very inefficient. And instead, when you're just given the xy coordinates like this, probably the easiest thing to do is to just apply the slope formula. So the change in y essentially means what is the difference between my two y coordinates. This is commonly given as y2 minus y1. You could flip these. You could say y1 minus y2. Ultimately, what matters is that whatever the order is, either 2 minus 1 or 1 minus 2, the x's and the y's have to be the same thing. So if your numerator is y2 minus y1, then your denominator has to be x2 minus x1. If you were to do y1 minus y2 in the numerator, that's fine, but then it means that your denominator would have to also be x1 minus x2. So again, it doesn't really matter which one you choose, but you have to choose one and kind of stick with it. So going back to my coordinates here, -3 is x1, 7 is y1, that's a y. Let me just erase that. So y1. -5 is x2, and 17 is y2. And now we just plug them in. So y2 is 17, y1 is 7, and remember we're subtracting, so it's minus 7. x2 is -5, and x1 is -3, but we're subtracting it. So when you subtract a negative, what you're kind of really doing is you're adding. So I would strongly encourage, instead of saying minus negative, just go ahead and make that flip. It's just easier to work with. So now we just evaluate or simplify the numerator and the denominator. 17 minus 7 is 10. And -5 plus 3 is -2. And 10 divided by -2, well, that goes evenly, and that becomes -5. And that is our answer. Next question is number 2. So our slope, once again, y2 minus y1 over x2 minus x1. It is the change in y over the change in x. And 12 is x1, -37 is y1, 4 is x2, and -3 is y2. So y2 we just said is -3. y1 is -37, but we're subtracting it, so we're going to add 37. x2 is 4, and x1 is 12. And again, we're subtracting. -3 plus 37 is 34. And 4 minus 12 is -8. Now, we have a positive over a negative, and so we know our answer is going to be negative, and you don't want to keep the negative inside the fraction. So you want to pull it out. You don't want to leave it in the numerator or the denominator. You just want to make the whole fraction negative. Now, unlike number 1, with number 2, our final answer is going to be a fraction because 8 does not go evenly into 34. So we're going to wind up with a fraction here, which is very common when you're working with slope. If you want to reduce this fraction by hand, what we need to do is we need to identify what is the GCF of both 34 and 8. What is the greatest common factor? What number goes in evenly? What is the largest number that goes in evenly into both 34 and 8? Well, they're both even, which means they have at least a 2 in common. Now, if you divide out that 2 from 34, you get 17, and if you divide out the 2 from 8, you get 4. And 17 and 4 are, there's no more common factors. 17's prime, so it's unlikely that it would have a common factor with a number like 4. And so if you divide out a 2 from both of these, 34 divided by 2, like I said, is 17. And 8 divided by 2 is 4. So you end up getting negative 17 fourths. Now, if you're a little shaky on simplifying fractions, and if you are in a context where you have access to a graphing calculator, you might not always have this, but if you do have access to a graphing calculator, the graphing calculator can reduce fractions for you. It's kind of nice. So our number was 34 divided by negative 8. And then if you look on the left, the button that says Math, right below the alpha, the green alpha button, it says Math. If you press that, it brings up a menu that's got a whole bunch of stuff in it. And what's kind of nice is that literally the very first option under the Math menu, option number 1 is Convert to Fraction, and specifically convert to a fraction in simplest terms. So if you press Enter, that says, all right, we'll take my number and convert to a fraction. So if I press Enter one more time, it actually will do the simplification for you, which is kind of nice. So negative 17 over 4. But again, if you want to do this by hand, or if you more likely have to do this by hand, what you want to do is you want to divide out the GCF from both the numerator and the denominator, which in this case was 2, giving us negative 17 over 4. You can also express this as a decimal. Negative 17 fourths is also negative 6.25. And in the absence of any other context, both of these answers would be acceptable. So either negative 17 fourths or negative 6.25. Number 3, M is, as always, y2 minus y1 over x2 minus x1. Negative 11 is x1, negative 24 is y1, 21 is x2, and 40 is y2. So y2 is 40. y1 is negative 24, but we're subtracting it, so this becomes a plus 24. x2 is 21. And x1 is negative 11, but again, we're subtracting it, so we're going to say plus 11. 40 plus 24 is 64. 21 plus 11 is 32. This works out pretty nicely. 64 divided by 32 is a nice round integer of 2. And so that's our final answer. Number 4. Oh, one day I'll stop doing that. M is, as always, y2 minus y1 over x2. That's an x. Let me redo that. x2 minus x1. 55 is x1, negative 75 is y1, negative 15 is x2, and negative 40 is y2. So y2 we just said is negative 40. Y1 is negative 75, but we're subtracting it, so we're going to say plus 75. X2 is negative 15. And X1 is 55, and we are subtracting it, so it's minus 55. Negative 40 plus 75 is 35. And negative 15 minus 55 is negative 70. All right, well, our denominator is larger than our numerator, so we're definitely going to get a fraction here. And again, we have a positive over a negative, and so when you express this as a fraction, you don't want to leave the negative inside the fraction. You want to just say the entire fraction is negative. And simplifying this isn't too bad because it turns out that 35 is itself a factor of 70. 70 can be written as 35 times 2. And so it actually turns out that in this case, the GCF of 35 and 70 is 35 itself. You can divide out a 35 from both of these terms. So 35 divided by 35, well, any number divided by itself other than 0 is 1. So my numerator is going to simplify all the way down to just 1. And then 70, when you divide out a 35, is 2. And so our slope is negative 1/2. And if you were to express this as a decimal, negative 1/2 is the same thing as negative 0.5. And so either one of these answers would be acceptable. The next problem is in the set section. For problems 6 through 13, use the following situation. Adam and his brother are responsible for feeding their horses. In the spring and summer, the horses graze in an unfenced pasture. The brothers have erected a portable fence to corral the horses in a grazing area. Each day, the horses eat all the grass inside the fence. Then the boys move the fence to a new area where the grass is long and green. The brothers have always arranged the fence in a long rectangle with 10 feet by 70 feet for an area of 700 square feet. Adam has learned in his math class, oh, look at him, that a rectangle can have the same perimeter but different areas. He is beginning to wonder if he can make his daily job easier by rearranging the fence so that the horses have a bigger grazing area. He begins by making a table of values. He lists areas of rectangles with a perimeter of 160 feet. He realizes that a rectangle that is oriented horizontally in the pasture will cover a different section of grass than one that is oriented vertically. So he is considering the two rectangles as different in his table. Question 6 says, fill in Adam's table with all of the arrangements for the fence. The first one is done for you. That's nice. So we have a table here with 4 columns. First column is the length in feet. Options go from 10 to 70, increasing by 10 every time. Second column is the width in feet. The first one's done, but we're going to have to fill out the rest of them. The perimeter is in the third column, and notice that the perimeter is not changing. So Adam and his brother only have so much fencing. Specifically, they have 160 feet of fencing, and that's not going to change. So no matter what size rectangle it is, they're kind of locked into using the 160 feet, no matter what shape it is. And then the fourth column is the area. Now notice that length, width, and perimeter are all given in terms of feet because length, width, and perimeter are all one-dimensional units of measurement. Area is a two-dimensional unit of measurement, so those units are square feet or feet squared. And again, we can see here that the first one was done for us, and so the 10-foot by 70-foot rectangle has an area of 700 square feet. Now, we have to fill in this table. The next entry is, well, what happens when the length is 20 feet? Well, if the length is 20 feet, we've got a rectangle that looks, I'll do this over here on the right. We've got a rectangle that looks maybe something like this. And the length is 20. And one of the properties of rectangles is that opposite sides have equal lengths, which is quote unquote obvious. So if that's 20, then this is also 20. And we don't know the width. So whenever we don't know a value, one possible strategy is just label it. We'll just label it as x. Actually, you know what? We don't always have to use x. We'll use w, because that's the width. So w and w. Now, we know that the perimeter is 160. That does not change for every single rectangle in this table. So if the perimeter is 160, perimeter is the sum of all of the sides of a polygon. And so a rectangle has 4 sides. And in our picture, those 4 sides are the top, the bottom, the left, and the right. That's what perimeter is. It is the sum of all of my side lengths. So I have an equation here that I should be able to solve. So the 160 is going to drop down. 20 plus 20 is 40, and w plus w is 2w. All right. We want to get w by itself, so we will subtract 40. Subtract 40. 160 minus 40 is 120, and the 2w drops down. I want to get rid of that 2, and the 2 is being multiplied by the w, which means I want to divide. I want to do the opposite of that. So those 2's are going to go away, and 120 divided by 2 is 60, is w. And if you want to go back and check this, it's relatively easy. If you plug in a w back into our original equation, you get 20 plus 20 plus 60 plus 60. And if you go ahead and do that, you will in fact get 160. So our width, when the length is 20, our width is 60. 60 feet. Perimeter is still 160, obviously, and the area, well, the area of a rectangle is length times width. So if our length is 20 and our width is 60, 20 times 60, well, 2 times 6 is 12. And then I've got a 0 and a 0, so I'll just slap those at the end. So 20 times 60 is 1,200 or 1,200 square feet. All right. Now, for 30 feet, we could very easily do what we just did and sort of redraw the picture and get an equation and solve it and do all that again. But there's got to be like an easier way of doing this. Notice that in the first example, when our length was 10, our width was 70. 10 plus 70 is 80. Which just so happens to be half of the perimeter. In the second row, our length was 20, and our width was 60, and 20 plus 60 is again 80, which is half of the perimeter. And if you think about it, this should make sense, because if going back to our picture for a second, if we replace these w's with 60s, say w in this case was 60, well, if you take one of your widths and you take one of your lengths, right, this is 80. And then if you take the other one, the other pair, that's also 80. And 80 plus 80 is 160. So, and the same thing was true with the first example. The length was 10, the width was 70. If you take one pair, like one length and one width, you get 80. If you take the other length and the other width, you will again get 80, which will add to 160. So it actually turns out that this is this width column is going to be relatively easy to fill in, because the length and the width have to simply add to 80 every single time, because you'll get 80, and then another 80, and that gets you the 160. So we don't have to do all the algebra that we did for the 20 feet. If the length is 30 feet, we can just jump right to the width and say, all right, well, 80 minus 30 is just 50 feet. And if you want to double check this, your perimeter is going to have two lengths and two widths. So it's going to be 30 plus 30 plus 50 plus 50, which is, in fact, 160. If you don't believe me, go ahead and check for yourself. But the length is going to be, if the length is 30, then the width is 50. So the area is still, we're still multiplying. So 30 times 50. So 3 times 5 is 15. And then again, there's a 0 from the 30 and a 0 from the 50. So we can just kind of slap two zeros there at the end. And we get 1,500 square feet. Similarly, if our length is 40, well, 80 take away 40 is 40. And 40 plus 40 is 80, another way of looking at that. Our perimeter, well, it's going to be 40 plus 40 plus 40 plus 40, which is 160, so that checks out. And when I multiply 40 times 40, 4 times 4 is 16, two more zeros, square feet. Now, when our length is 50, notice that when our length was 30, our width was 50. Well, if our length is 50, it's pretty straightforward to see that our width is going to have to be 30. You're really just like taking the third row and just sort of like flipping the length and the width. And multiplication is commutative, so the order doesn't matter. So 30 times 50 is the same thing as 50 times 30, which we already found was 1,500. So we know that this has to be 1,500. Or 1,500, however you prefer to say that. Likewise, a length of 60, well, that's going to correspond pretty nicely to when the length was 20 and the width was 60. So now the length is 60 and the width is 20. We already did this multiplication, and we got 1,200 square feet. And finally, 70 feet. Our width is going to be 10 feet. And 70 times 10, this is actually the one that they gave us, which is 700 square feet. Question 7. Question 7 says, discuss Adam's findings. Explain how you would rearrange the fence so that Adam will be able to do less work. With a kind of an open-ended question like this, the way that you want to phrase this, you can include any number of pieces of information here. The way that I would say this is I would say as the length and width, go ahead and change my box size, bring this over and down. As the length and width approach 40 feet, the area approaches a maximum of 1,600 square feet. I'll just type it out, I guess. Square feet. And explain how you would rearrange the fence. So Adam should rearrange, not typing very well today, should rearrange the fence into a 40 feet, go ahead and make a new line here, into a 40 feet by 40 feet square. Question 8. make a graph of Adam's investigation. Let length be the independent variable and area be the dependent variable. All right, so that means, so we're going to let length be the independent variable. The independent variable on the coordinate plane is x, is the horizontal axis. That represents the independent variable. If you're talking about a function, the independent variable is the input of that function, commonly x. And then area is the dependent variable, which is going to be y. Again, if you're talking about a function, it is the result of evaluating the function, right? You plug in an x and you get y. So length is going to be independent, area is going to be dependent. Label the scales so all points from the table show on the grid provided. All right. Let's start by getting some axes on this graph. Now, for this problem, I'm going to arrange my x and y axes so that our graph is almost exclusively focusing on quadrant 1. So I'm going to put my x-axis all the way at the bottom of this graph, and I'm going to put my y-axis all the way on the left. And what that's going to do is it's really going to highlight quadrant 1 in this case. And the reason is because in the context of the problem, we're talking about length and area. And it doesn't really make sense to talk about negative length or negative area. And that is what would be represented in quadrants 2, 3, or 4. So again, I put the axes here just to sort of maximize the space on what we sort of really care about, which is quadrant 1. And this is actually very common in a lot of real-world scenarios. Not all. Occasionally negative numbers do in fact make sense. But in this context, they really don't. So that's why we want to set up our axes this way, just to give us the most amount of space to sort of work with. So our x-axis is the length. And our y-axis is the area. Now, for our scale, for the length, our table, the largest length that was on the table was 70. However, I think it's going to be a good idea if we also, at least for our graph, include 80. Because with 80 doesn't really make sense in the context of the problem, because if the length is 80, you're going to use up the entire 160 on your two lengths, and you're not going to have any left over for the width. So you're not really going to have a rectangle at all. You're going to have like a straight line. You're going to have like just two pieces of 80-foot fence that are like next to each other, but there's not going to be any space in between them. But I think for the context of the graph, it'll be good if we can actually see sort of like what would happen at 80. The area is going to become 0. Likewise, if the length is 0 and the width is 80, it's going to be the same thing. Our area is going to essentially be 0. But I do think it's going to be good to include 80 on the length. So I think if we treat every 2 boxes as 10, or every box is 5, I think that will fit. So if we do 10, 20, 30, 40, 50, 60, 70. Yeah, it just barely fits. So we can go ahead and label. We'll label each one of these. So 10, 20, 30, 40, 50, 60, 60, 70, and 80. All right. For the area, looking at our table, the largest area was 1,600. So we want to be able to fit 1,600 on this scale. And if we treat each box as 100, let's see if that'll fit. 1, 2, 3, 4, 5, 6, 7, 8, 900, 1,000, 11, 12, 13, 14, 15. Again, that barely fits. So I think this is probably what they want us to do in this space. So the top one's going to be 16. Now, labeling like every single hash mark here is going to get a little crowded. So I'll label every other one. I think that'll be sufficient. So this is going to be 200. This is going to be 400. This will be 600. This will be 800. 800. 1,000. 1,200. No. Go away. I said go away. Let's 1 second. There we go. 1,400. And then the very top is going to be 1,600. All right. And I think that is everything. And now we just need to actually plot the points. So looking at our table, I'm not going to go back up to it on the screen, but you're welcome to take a look at the table on your paper. So when the length was 10, when the length was 10, the area was 700. So 10 and 700 is right. 10 and 7 is right there. So when the length was 10, our area was 700. When our length was 20, our area was 1,200. Right there. Length was 30, area was 1,500. Length was 40, area was 1,600. Length was 50, area was 1,500. Length was 60, area was 1,200. Length was 70, area was 700. And like I said, we didn't really calculate what would happen when the length was 0. But if the length is 0, then the area is 0. So we can include the origin here, bottom left. And then if the length is 80, then the width has to be 0. There's no more fencing left over for the width, which means the area will again be 0. So I guess technically maybe those dots should be open dots, but I think it's fine for now. And the only thing left is actually to connect these points, because we can connect these points because even though our table only talked about like specific lengths, like 10, 20, 30, 40, there's nothing preventing them from making a fence that's got a length of, like, let's say 35 or 37 or 52.6, right? I mean, we could have lots of different combinations here, not just these dots. So because of that, we really should connect these dots, because there's really nothing preventing them from having, lengths that are not powers of, or multiples of 10, and they could even have decimals if they wanted to. So if we go ahead and connect these, hold on, go back and make that back to 1. So if we connect these, something looks like that. And that is our graph. Number 9, describe the shape of your graph. So again, the way that you might phrase this might be a little bit different, but for me, what I would say is the graph is an upside down parabola. Change the size. Okay. So the graph is an upside down parabola with x intercepts at x equals 0 and x equals 80. and a maximum at 40, comma 1600. So I think that pretty much describes our graph pretty well, right? It's an upside down parabola. It intercepts the x-axis at 0 and 80, and it's got a maximum at 40, comma 1600. All right. Question 10. Write an equation for the area based on any given side length x of fence for the rectangle, on any given side length. So we want an equation here. So as a we'll use function notation here, and the name of the function we'll call capital A. So this is function A, and it's saying that our input is going to be x. So we're going to say A of x. This is our area function, our area equation. And in this case, x represents the length. And we know that the area of a rectangle is length times width. So if our length is x, we know that it's going to involve x, right? That's our length. Now, for the width, what we do not want to do is we do not want to introduce a second variable here. We do not want to do this, right? We do not want to say x times w, because if at all possible, we want to use as few variables as possible. And when you introduce a second variable, things get significantly more complicated. And in this context, it's not going to work. So we do not want to represent the width with a second variable. What we want to do is we want to represent the width in terms of the length, which again was x. So if you think back to our table, and maybe we'll go back to it real quick just to see this. Don't forget, when we looked at our table, every single time the length and the width would always sum to 80, every single time. And we discussed why when we filled in this table. So if the length and the width always sum to 80, and if our length in this case is given by x, then our width is going to be 80 minus x. Whatever our length is, our width, we can take 80 and subtract our length, and that is our width. So if our length is 10, our width is going to be 80 minus 10, which is 70. If our length is 60, then our width is going to be 80 minus 60, which is 20. Right? If our length is 16.4, then our width is going to be 80 minus 16.4, which is 63.6, I want to say. Something like that. But anyway, you get the point, right? So our length is x, our width is 80 minus x. You could leave your answer like this if you want to. You could also distribute if you want to. And if you distribute an x here, you get x times 80, which is 80x. And x times x is x squared, and we're subtracting, so this is minus x squared. So either version here is fine. I think that there's actually pros and cons to distributing, so I think either version would be acceptable. Question 13, explain what makes this function a quadratic. So there's actually a lot that you can say here. So I don't think that you would need to include everything that I am about to type, but you should include maybe like one or two of them. So what makes this function a quadratic? Well, one thing that makes it a quadratic is that the graph is a parabola. So when the graph of a function is a parabola, well, that is equivalent to saying that you have a quadratic function. Those are two ways of saying the same thing. Either the graph is a parabola or you have a quadratic function. Those are equivalent statements. So the graph is a parabola. That tells us it's a quadratic. The second differences are the same. Right? So the second differences of this function are the same, and so that is another way that this is a quadratic. The equation has a product of two linear factors. So we saw that in question 10, right? We have, in this case, we have one linear factor, which is x, and we have another linear factor, which is 80 minus x, and we are multiplying those two things together. That tells us that our result is going to be a quadratic. Also, the highest power of x is 2. And we saw that when we distributed. So that is right here. So because the highest exponent on x was a 2, so this was a 1, we didn't write that 1, but it is there, and the other one is a 2, and so because the highest exponent is a 2, that is another way of telling us that this function is a quadratic. So all four of these sort of indications are accurate. So the graph is a parabola, the second differences are the same, the equation is a product of two linear factors, and the highest power of x is 2. All of those things indicate that we are talking about a quadratic. The next problems appear in the Go section, and the directions here say determine which function will be increasing faster when x is very large. So the first assigned problem was question 16, and the directions ask what's going to happen when x gets very large. So what that is saying is if we were to extend this graph to the right, okay, so the horizontal axis, the x-axis, as you go to the right, x gets very large. So you would expect over in to the right here that x would be a large number. And it's basically just saying what's going on over here. Right? What's happening with these two functions when you go way to the right? Now, both of these functions, m of x and n of x, these are both linear functions. And we can tell that because the graphs of the functions are themselves straight lines. So when you have a straight line, we're talking about a linear function. And the thing with linear functions is that the rate of change, which is the slope, the rate of change itself does not change. So whatever the slope is, it's going to be the same slope, whether you're talking about the extreme right or the extreme left or the center. It doesn't matter. A straight line has the same slope no matter where you're at. And again, we're being asked to determine which function will be increasing faster. So we can tell just by looking at this line here that the slope of this line it's steeper than the slope of this line, right? M of x starts actually below n of x, right? But then they intersect here, because m of x, even though it starts lower, it's increasing faster. And then once they intersect and then continue to go, m of x is above n of x, and that's just going to continue as you go to the right. So for 16, our correct answer here is that m of x is going to be increasing faster, not just on the right, but throughout the entire graph. m of x is increasing faster because these are linear functions, and m of x has a larger slope than n of x because m of x is steeper. Now, for 18, 18 is a topic that is covered in the new Math 1 curriculum. However, if you did not take the new Math 1 curriculum and you're coming directly into Math 2, this question might look pretty unfamiliar. So if that's the case, that's fine. This is all about practice. So in this case, it turns out that both f of x and g of x are what are called exponential functions. Now, exponential functions are an entire topic that we don't have time to go into right now. But again, the directions are the same as before. Determine which function will be increasing faster when x is very large. So again, we're talking about what's going to happen. What's going to happen when we go all the way to the right here? Which function, f of x or g of x, is going to be increasing faster? So if you look at the pattern or the path for f of x, notice that f of x starts below g of x, right? This is below the other line. I just made a straight line. That's not what I want. Go away. All right, I'm going to have to do it a little bit faster. I don't want this to form a straight line. So f of x, it starts below it, but then it passes g of x and then starts shooting up. Meanwhile, g of x starts out above f of x, but then it gets surpassed by f of x, and then it also starts to go up, but not before f of x sort of like overpowers it. And again, this point of intersection kind of tells us what's going on here. When you have this with exponential functions, when one of the functions, f of x, when it starts out below the other function, in this case, when it starts out below g of x, but then it surpasses it and then it increases faster, it turns out that in this case, let me redo that. F of x is the function that when you're over here, it's going to be increasing faster because it's sort of like, to use a metaphor, it's sort of like it put its foot on the gas earlier. It started out kind of slow, but then its rate of increase started earlier. And so it turns out that f of x is actually going to be increasing faster once you get further to the right than g of x. And again, if you haven't really worked with exponential functions very much, this is just one of many topics dealing with exponential functions. So if this was a new topic for you, this is how we evaluate this kind of question. When we're looking for which function's increasing faster, and we're comparing exponential functions, which is what we have going on here, the graph that starts increasing faster, which in this case is f of x, is eventually going to be the function that is increasing the fastest when we go all the way to the right. If you did not get 18, but you just watched the answer for 18, and now you're looking for 19, I would definitely encourage you to try to answer 19 before watching this video, because they're very similar questions. 19 is, again, we are looking at two exponential functions, p of x and q of x. And we can see that with p of x, we start out below q of x. It then intersects q of x. It essentially catches up to it, and then it starts going off to the right, or going up, rather. Q of x starts out above p of x, but then it kind of gets caught, and then it also starts to increase, but it starts to increase a little bit after p of x does. if we treat this box as like if we say like x equals 1 in this case, if you look at red, red is increasing. If we focus on like this piece right here, red is increasing pretty quickly at 1, whereas green is still kind of tailing off. It doesn't really start to increase until once it hits maybe 2 or like 2.5. So because of that, as we saw with question 18, because p of x starts increasing faster earlier, it turns out that when you go pretty far to the right, p of x is going to be the function that is going to be increasing faster. So the correct answer for 19 is p of x. Last one, question 20. We have a graph here. We have r of x and s of x. Before we even get to the questions, it's probably worth kind of orienting our mind as to what we're talking about here. So r of x, which we'll do in red, r of x is this guy. And s of x is this guy. These are clearly two different types of functions. Right? One of them, s of x, is a straight line. So s of x is linear, whereas r of x is definitely not linear. And it turns out that r of x is an exponential function. And again, if you did not take the new Math 1 curriculum, chances are probably maybe unfamiliar with exponential functions, which is fine. But if you take a look at the graph here, we actually don't necessarily need to know much about exponential functions in order to answer these questions. 20A is saying, examine the graph from 0 to 1. So I'm actually going to erase all this for a second. And I'm really going to zoom in here. Zoom in 500%. That works. So we want to know what's happening between 0 and 1. So I think we can safely assume that this is 0 and that this right here is 1. So we're looking at, what's happening here, basically. And r of x is our exponential function. That's the curved one. So if I only trace the piece of r of x that is between 0 and 1, it's this piece right there. That's r of x. S of x is this piece right there. And the question is, which graph is growing faster in this interval? Well, it looks to me like both of these graphs, it looks like they both intercept the origin. They both go through 0, 0. So they actually both start at the same spot. But between 0 and 1, they both start at the same spot. And r of x, which is the exponential function, which is the red piece, once you get to x equals 1, it seems to stop maybe right about there. And meanwhile, s of x, the straight line, the linear function, seems to stop right around there. And so we can see that if we want to know which one is growing faster between 0 and 1, well, notice that green is above red. So let's see if we can get this back to normal. Go back to 200%. Bring this over. I'm going to clear out this. Let me actually change all these back before I forget. So this is to 1. This is to 1. And that's to 1. Okay. So which graph is growing faster between 0 and 1? It looks like the linear graph is growing faster, which was s of x. 20b says, now look at the graph from 2 to 3. Which graph is growing faster in this interval? So again, we'll look at, well, actually, I'm not going to zoom in this time because I don't think it's quite necessary. So 2 to 3, so 2 is there and 3 is there. So we are looking at what is happening here, right, in this area. And if I look at, we'll look at s of x first. I guess I didn't have to, could have kept these as dots. So if I look at s of x looks like it starts there and ends about there. And meanwhile, again, go back up to 4. R of x starts out above s of x. But we actually don't even see where r of x intercepts at 3. It looks like it might be like there, maybe. You know, if we were to continue this, maybe it hits 3. You know, right about something like that. You know, regardless of where you sort of estimate this, between 2 and 3, I'll extend the highlight here, right? This is all between x equals 2 and x equals 3. It certainly looks like r of x at this point is now increasing faster, regardless of sort of where you estimate that second red dot to be. Once you're between the 2 to 3 interval, r of x is clearly increasing faster than s of x. So for 20b, the function that's increasing faster, growing faster between 2 and 3 is r of x.